Hello everyone, and welcome again to this new lecture, and let us quickly come to the point what we have to do. And if you remember, we are doing or in calculating the stability condition and the value of n for which, and n is the power to the potential, r power to the r of the potential, that for which the orbit is going to be a stable orbit, or rather we were calculating for this circular orbit. So if you remember that we had calculated that for f is equal to minus kr to the power n, and then this is going to be greater than n value is going to be greater than minus 3. So to uh, this orbit has to be a stable or circular orbit. And if potential is been given, then you can calculate the condition of n. For example, if you see that this potential, that is for what value of n are the circular orbit be stable with the potential. If this is potential is given and the centrifugal energy is also given, b bar minus r2 is also given, where b is greater than 0. So my effective potential is basically this Vr plus what we call is L square by twice m r square. So this is given as Br minus 2 in our case. Okay, so this is effective potential. So if this is the potential is given, so the question is to what is the value of n for the circular orbit to be stable under this potential. So you know that you have to calculate first that you have to differentiate with respect to r at r equal to r naught, where the circle is going to be the circle, and then you differentiate it, double differentiate it, and put in the condition that is going to be greater than 0. Okay, and similarly this is show that the potential is given, that the orbit is closed and stable. So this is for example, let's try to do this, and this is v. So v effective in our case, is going to be Vr plus L square by twice mr square. So Vr is given to us, that is half kr square, and this is L square twice mr square. Okay, so if we do the first differential, what I'm going to get is that is ddr of half kr square plus ddr of L square by twice mr square, and this is at r equal to r naught, this whole. Okay, at r equal to r naught we had to evaluate it. So this is what is going to be, this is going to be half k and ddr of r square at r equal to r naught, and plus this L square by twice m I can take common, so this is ddr of 1 upon r square at r equal to r naught. Okay, so this if I go from this side to this side, so you can say that this is going to be my this is square, so this is going to be half k into twice r at r equal to r naught, and then you have plus L square by twice m, and what you have 1 by r square is going to be minus 2 by r cube. Okay, this is going to be minus 2 by r cube at r equal to r naught. So this is going to be 2 will cancel out, this is k r naught at put r equal to r naught plus this is going to be minus, this is going to be minus, this all is going to be 0 because this is ultimately is going to be 0. So this is going to be minus twice will cancel out. So you have L square upon m r naught cube. Okay, this putting r is going to be 0. So from here you can put the value, get the value of r naught. So if you multiplied by r naught cube, if I multiplied this with r naught cube, so this r naught will cancel out, and then you have r cube, this r4. So what I'm going to have is r naught is 4 equal to 0. Okay, so k r naught no, it's not 0, it's k r naught. This is going to have k r naught 4 minus this is L square by m is equal to 0. So from here you get k r naught 4 equal to L square by m, or r naught 4 you are going to have L square by mk. This is I'm going to use here for this condition. Okay, now I'm going to find this d2r. So d2r upon r naught. So this is what I find in case of uh, what is dv by dr. My dv by dr is kr naught. So my dv by dr was kr naught minus L square by mr naught, mr cube. So this is mr cube, L square by mr cube. This is my dv by dr here when you plot. Now I have to double differentiate it. If it double differentiate is d2v upon dr square. Okay, so this is going to be k. Okay, because with r is going to be k, and then minus this is going to be L square m, and this r cube is minus 3 upon r4. Okay, and then this is minus 3, and this has to be greater than or equal to 0. This has to be greater than or equal to 0. So this is going to be k, and this minus minus plus, this is going to be 3 L square upon mr4 is greater than or equal to 0. Now this has been calculated. R is equal to r naught. So at r is equal to r naught, if I put r equal to r naught here, this value, so what I'm going to get is here at this position, this is k plus 3L square upon 3L square upon m, r naught 4 is greater than 0, and r naught 4 is L square by mk. So I can put it here. This is going to be k plus 3L square m, r naught 4 is L square by mk. This is going to be L square by mk is greater than 0. So will cancel out. So L square cancel out. So I have what is k plus 3k. So this is going to give k plus 3k is greater than 0, or 4k is greater than 0. So 4k is greater than 0. So this is going to be for a condition for the stable orbit. Okay, so this orbit for this potential is going to be 0 when this 4k is, or k is always greater than 0. That means the k has to be greater than 0. The restoring force, that is the potential corresponding to this is force corresponding to this is u. So this is minus kx. So this k is always going to be positive, otherwise this becomes kx. So then this is not going to be the restoring force. So this is the condition for this. In the same way, you can find, in the same way you can differentiate it. And you can find the condition that n is going to be minus 3. This is straightforward. You can do this one exercise here. So now with this I'm moving for the second topic of this lecture, that is the scattering in central force field. So before discussing the real scattering, that we are going to take into consideration the Rutherford scattering of the alpha particle with the nucleus, and before that we need to clear some nomenclatures related to a scattering and the cross section. So basically you can see that these are the particles. These are the particles which are incoming particles, and then they are they are striking the target. This is my force center, and these particles are coming and then striking the target, and then something will happen depending upon the conditions, the charge of the particles, and all these. So we are not seeing the original. This is two body problem, because the one body, that is the constituents of the projectile which is coming towards the target, and the second body is my target nucleus. So this is like alpha particle is one body, and then the nucleus, the gold nucleus, is the second body. So this is two body problem as an equivalent to the scattering of the particle with reduced mass from a center of the force. So we have already done this two body problem reduced to one. So now if you consider a uniform beam, this is a straight line, this uniform beam of the particle, all of the same mass and energy on a center of the force. So if we have a particle which is coming towards the target, that you consider that all these particles have the same mass and the same energy, which are moving towards the center of the force, moving towards the target. Okay, or if this is a positive particle and a positive particle, and this is also positive, so this is going towards this, so it's going to have certain energy about that. Otherwise, this not going to reach to the nearest approach of that target. And then assuming that the force between an incident particle and the particle at the center, where this is the center where this particle is coming and trying to hit it, falls to zero at the largest distance. That means the force is of 1 by r square type. So at the particle is going away from the center of this, so then this is going to be the force is going to be less and less and less and less. It's going to be finally is going to be 0. Okay, so then 0 at large distance. And then we define a quantity that is known as the intensity, or the flux of the incident beam, or intensity of the incident beam. These beams, this projectile which is coming, so what is the intensity of that projectile, or what is the flux of that projectile? So that means flux is, or intensity is basically the number of particles crossing per unit area, number of particles crossing perpendicular area, that means perpendicular per unit area per unit time. So whatever the area is there, if you choose certain area when these particles are going, if you choose a perpendicular area, so per unit area per unit time, what is the number of the particle which is crossing is basically the intensity or the flux of that beam. Okay. The second thing is consideration in scattering is that as the particle approaches the center of force, so it will be either attracted or repelled, because if it's positive particle, if this is positive target, then it will be repelled back because plus same charges. If either of two is of the different charges, then they will be attracted towards and they will be going to have the collision. Okay, so then that will decide the trajectory. Okay, so depending upon the charge of the particle and the approach of the particle will decide that it is going to repel or scattered or going to have the hit on collisions. So then the trajectory, if this is positive, then the trajectory which is coming is going to be deflected from its the straight line path. So if the particle is this is positive, and this particle is also positive and is coming, so if it is going, if it's not will not be a straight line, because as it approaches towards this potential of this positive charge, it's going to get deflection. Okay, so either from this side or this side. Okay, as it is reaching towards it, is going to be deflected towards it, and as it goes, the force because of this potential is going to be 0, and then again then this particle going to have a straight line. Okay, straight line. So earlier it was coming from infinity, is going to have a straight line, and then within the vicinity of that particular potential, it deflects its path, and then after at large distance is again going to have a straight line motion. So after passing the center of the force, the particle goes away, the force acting on it will decrease because at large distance finally, and the force will become 0. This results again in the straight line motion, but in different directions. So in general, this final direction of the motion is not the same as an incident direction, because like if you suppose that it's going here and then scattered and then from there goes again like this, in general it's not possible, because if once it deflected, and that is will go somewhere else. So such phenomena is basically is said to be the scattering of the particle from the scattering center of the force. Okay. So and then the important thing we can define is the scattering cross section. So intensity was the initial flux, or intensity was the number of projectile particle which are coming towards the force center, and if you consider some cross section then perpendicular to this, then the what number of the particle which are going through this perpendicular distance per unit time per unit area is going to give you the intensity or the flux of the incident beam. Now cross section is something which experimentally you calculate is so if you consider a uniform beam of particle moving with flux, say I say some intensity, some so I naught, whether you can I and I naught, whatever it is, this is the incident beam are coming, and that is the flux of this towards the scattering center, that is what is going to be the atom or the target. So imagine that the scattering center present an area d sigma, okay. So perpendicular to the part of the beam such that whatever hit the particle hit the d sigma area and they scattered into a solid angle d omega. So if you consider this area df area, this is d sigma area of what of the target of this. So if I have a target, and if you consider d sigma area of this target, say this d sigma area of this target, okay. So then these particles which are coming, this area has to be perpendicular to this, okay. And then when hit this is when hitting this d sigma area, okay, when these particles which are of same mass and same energy are coming, and some will not hit, some will hit this. So when this going to hit it, like that means to moving towards the center, depending upon if this is positive charge, this is positive charge. So then these all particle are basically not going to hit it because these are all positive, this is also positive. So then it's going to scatter into a solid angle. Okay, from here it will going to scatter into some solid angle. So this is going to be my d omega. Okay. So this is going to be scattered into some solid angle from here and here and here, whatever the direction it is coming from these initial direction. So these are going to be scattered into some solid angle. So what we are imagining that the scattering center present an area d sigma away perpendicular to the part of the beam such that whatever particle hits the d sigma is scattered into a solid angle. Okay. So solid angle is nothing but like in your circle, this angle is if particle goes from this position to this position, from this so this angle is or if particle goes from this angle to deviate from this to this angle is theta. Similarly, if you have a sphere, then this is going to be a kind of cone. Okay, this is the solid angle. Then you have a number of particles, so that is d omega is whatever the omega angle, this is just the element of that omega direction in which the omega is the direction in which the angles, the particles are being scattered, and d omega is the element of that solid angle. And the number of particles scattered into d omega solid angle per second. So what is the number of particles scattered into d omega solid angle per second? Because I naught is the intensity, is the flux per unit per second, per unit area, per unit time. So this is per unit area, per unit time. So per unit area I naught is there. If I multiplied by the total area through which they are going, then this is giving me the number of particles scattered into the solid angle, because I naught is per unit area. So if I multiplied with the total area through which it is hitting and going, so that much of particle is going through this solid angle. And then second thing is the number of scattered particle in a small solid angle d omega about omega directions. So that is this is going to have this I times the d omega. This is very natural. So a scattered particle, whatever the particle is being hitting this area d sigma, and that they are going to scattered in this d omega angle, this d omega angle, this is d omega angle here. Okay, this is this d omega angle about this omega direction. Okay, so that is going to be have I omega and d omega. So and then where I omega is the intensity of the scattered particle, that is number of particle scattered in the direction per unit solid angle per unit time. This is what as such as I naught is the incident per unit area per unit time. Now the scattering is through the certain angles, so that area is now is in terms of the angles. So per unit solid angle per unit time. Okay. So because whatever the number of particle, this is I naught d sigma is hitting the target, and this is the same number of particle is going to be scattered from the target. So this I naught d sigma I can write is I omega d sigma. Okay. And from here I naught d sigma to I naught d sigma is I omega d omega. So I can write it d sigma by d omega is I omega upon I naught. This is number of intensity of the scattering flux, and this is flux incident. And so this quantity is known as the differential scattering cross section, that is, or simply a scattering cross section for the scattering in direction solid angle omega. Or so I can say that sigma d omega is the number of particles scattered into the solid angle d omega per unit time, and divided by this incident intensity or the incident flux. And if you integrate it, this total cross section over or whatever the solid angle is, then this is going to give me the total cross section. Two more important thing is, one is scattering angle, that is the angle between the incident and the scattered direction. So if I have this force, center of the force, and the particle is coming, this is my particle, if this is center of force, if this particle is coming, so if it's going to without any deflection, there is the angle is pi. But if this particle is coming, and because of this is positive charge, this is positive charge, this is going to get deflected from its original path. So this angle is going to have some theta, that is known as the scattering angle. That is basically, if you draw a asymptote from along this line from there, and you cut it where it chooses this angle with this original, is going to be your scattering angle. Okay, so this is what angle between the incident and the scattered direction of the particle is called scattering angle. Second thing is impact parameter, is defined as the perpendicular distance. Okay, so this is basically, if you can say that this, so many number of particles are coming from here and here and here, and this is my scattering center. So if you draw a line without scattered, and then what is draw a line perpendicular to from the scattering source to this the direction of this particle, this is going to be the impact parameter S. So defined as the perpendicular distance between the center of the force and the incident velocity. So the velocity direction is like this. So if you draw a perpendicular from this to incident direction, so this distance is going to be the impact parameter. Or we draw a perpendicular on the direction of the incident particle from the scattering center, then the length of the perpendicular is known as the impact parameter S. Okay, this is what is impact parameter. So you see that this is and these are, so for this particular particle, the particles are going so for this particular particle, this length is my impact parameter. This is distance from this the line which is passing through the scattering center. This is my scattering center, then the particles coming towards the scattering center, and they will get scattered. Okay, so the particle is coming, and this is my scattering center, will come and then will scattered in these directions. Okay, so this is differently is been shown. Okay, so and what else remains? So scattering angle is there, impact parameter we discussed. And one more thing we can discuss is this solid angle d omega. Solid angle is defined as the area divided by because this is the sphere where the surface is there. So that what is the radius of the sphere divided by the square of that radius, and this d sigma ds, not d sigma basically. So this is the area of this sphere through which we are defining this small solid angle. So as you can see here, this is my sphere. This is part of the sphere where you cut some. This is scattering center, and you cut this and this area. That is that how you define this ds. So this ds is basically this is your, if you cut this, then this is r is the distance, because you see this is scattering angle, this is my scattering angle is theta, because if a particle is coming and this is deflecting around the solid angle, okay, around this solid angle. So this is my angle theta, deflection from this incident direction, and then going around this solid angle. Okay, so this, if you see that this is going to be my if this is my r, so this is going to be r sine theta, and this thickness is also going to take place because this is going to be r, whatever is the r, and then what is this is a small angle d sigma from here to here. This is, if particle goes from either from this side or either from this position, this is the small solid angle that is going to be scattering angle, sorry, that is going to be d theta. So this arc is length is going to be the r times d theta. This is my r, and this is going to be the d theta. Okay, so that means this is around this you have a circle, like in this case you can see that around the scattering center I have a circle of a sphere, and then around a sphere these particles are being deflected. Okay, so what is this is like I'm considering this this, if you consider this as distance, or this distance, this is going to be whatever this r, this is going to be always, because this r and all these r is the radius of this sphere, so this is going to be r sine of what is scattering angle theta. Okay, so this is r of a scattering angle sine theta, and then this is also there r d theta multiplied by twice pi. So twice pi r is the circumference, and then multiplied by this r d theta thickness. So twice pi r sine theta is the circumference, and multiplied by the thickness is going to give you this ds, what you have considered area, and then divided by this r square. So this is twice pi sine theta d theta, and d sigma is so the area when this particle is going to strike at perpendicular distance of the effective target area is twice pi. If you see, this is so if you see, I explained this. This is from here. This is the active area d sigma where the particles are coming and the hitting the target. So that is also going to be in a circular orbit. That going to be this twice pi r is the circumference, and the ds is going to be this distance here. And so this d sigma is the effective area where the particle is going while it is moving. It is in counter perpendicular distance, so that is twice pi s ds. So next lecture we will continue from here. So I'm going to stop this right now, and thank you very much.